All right, today we'll be discussing the shape of a graph, and that's going to tie together with inflection points, something that we discussed very briefly in the first video for this chapter. So today we'll get into that in a little more depth. So we know that the first derivative tells us whether the function is increasing or decreasing. The second derivative is going to tell us how it's increasing or decreasing. So it's going to tell us the shape, or sometimes we call it the curvature, of the graph f of x. So when a graph has this shape here, we call that concave down. I like to think of it as when we're moving from left to right, the curvature is in a clockwise direction. Another way to think of it is if we were to draw a tangent line to this curve anywhere, the curve would be below the tangent. Compare that to the picture below, which is concave up. I think of it as moving left to right. We're curving in the counterclockwise direction, or you could just say that the function is always going to be above the tangent line. Now, our function isn't always going to look like a parabola. Okay, we might just see a piece of that parabola. So, for example, this is a graph that's concave down. This is also a graph that's concave down. Think about the tangent lines, think about how it's bending. Just like we decided that a function would be increasing on the interval for which its first derivative is positive, and it'll be decreasing on the interval for which the first derivative is negative, we're going to say that a function's concave up or down on an interval. It's going to be concave down when the derivative is less than or equal to 0. It's going to be concave up when the derivative is greater than or equal to 0. And we're not going to say that a function is both concave up and concave down when its second derivative is 0. But we would say that whatever that x value is, that is the end point of a closed interval upon which the function is concave up, and it's an endpoint of a closed interval on which it's concave down. So simple examples here, just thinking about parabolas. The curve negative f of x is concave down every place, because what's the second derivative of that? Well, the first derivative is going to be negative 2x, and then the second derivative is going to be negative 2. So that's clearly f double prime is less than 0, because it's equal to negative 2 everywhere. And same thing for the graph below. That's going to have a second derivative of positive 2. So just like last time, we found the intervals where a function was increasing and decreasing. Now we're just going to find the intervals where the function is concave up or concave down. So this is our function, and we're going to take a first derivative, and then we're going to take a second derivative. And then we're going to make a sign diagram for that. It's equal to 0 when x is equal to 1/2. We choose a test point to the left and to the right of 1/2, putting that into this expression. Don't put it in the sign diagram for dy dx. Don't put it in the sign diagram for the function itself. You got to put it in the right place. Anyway, from here we see that it's going to be concave down from negative infinity to 1/2 included, and it's going to be concave up from 1/2 to positive infinity included. And we do the same thing with the bottom one. Whatever, it's a quotient rule, so it's a little more exciting. That looks fun, doesn't it? But in the end, we have here the second derivative does not exist when x is equal to 3. Actually, the function itself doesn't exist when x is equal to 3. We're going to get a vertical asymptote there, but it's going to be concave up to the left of it and concave down to the right of it. So points of inflection, we saw these briefly in the first video. Just like in the previous video, when we classified stationary points as being either a maximum or a minimum or a stationary point of inflection, when we identify a point of inflection, we will need to know whether it is stationary or non-stationary. And that's easy to tell from the graph, but remember, we're doing this without technology, so we're trying to identify this stuff when we can't see the graph. So it all comes back to sign diagrams. Now we're going to have the sign diagram of our second derivative, and we're going to see that it's going to change sign at a particular point. That's our point of inflection. But then we can compare that to the sign diagram of the first derivative to figure out what's going on. So in this case, where we have the stationary point of inflection, our sign diagram for f double prime is changing from positive to negative, since we have a change of concavity here. The first derivative sign diagram is negative, negative, so I know that it's always decreasing. Would it be possible to have the same second derivative sign diagram, but the opposite first derivative? Could this have been plus minus? It's not something that the IB is likely to throw at us, but we could imagine what this would look like. It would need to be concave up, but increasing, and then be concave down, but decreasing. So that would have a cusp. So we see we can figure out a lot about the shape of a graph just by considering these sign diagrams. Down below, the non-stationary point of inflection, our sign diagram for f double prime is going to indicate a 0 at a particular point, but our sign diagram for f prime will not. It'll have zeros at different points. So that tells us that this particular value for A is a non-stationary point of inflection. So to summarize, here it is. Again, if you're studying for the AP exam, you need to consider not only where the second derivative equals 0, but also where the second derivative does not exist, but also changes sign. And that's really the key here. We need to have a sign change of f double prime at the point. Just because the second derivative is equal to 0 doesn't mean that we have a point of inflection. As an example, say we have the function x to the fourth. We can calculate its second derivative, 12x squared. Clearly that's going to be equal to 0 when x is equal to 0. But when we consult the graph, we see that actually the graph is concave up the whole way through. So what's happening there? Well, it's a weird, super flat spot. I don't know. Fun fact, this is called a point of undulation. You don't need to know it. What you need to know is that it's not a point of inflection unless the second derivative changes sign. So putting this all together, we have stationary points and we have inflection points. Some stationary points are also points of inflection, but not all stationary points are, and not all inflection points are stationary. But if we consider the sign diagrams of f prime and f double prime, we can figure out what it is that we're looking at. So here's our first big example of putting this all together. We are going to, down in part E, sketch this cubic function. All right, so first we're going to find all the places where the derivative is equal to 0. That should be easy enough. We're going to take its derivative. We get a cubic. Conveniently, this is factorable. We take the x out and we get a quadratic left over. So our sign diagram for the first derivative is easy to work out. And this tells us that we have a minimum here at 0. And it looks like we're going to have a point of inflection here at 2, a stationary point of inflection. All right. Whoop. There we go. And we label the x and y values for each of these points simply by putting 0 and 2 back into f of x. Part B, find and classify all the points of inflection. We already found this one. 2 is a stationary point of inflection. Are there more? We're going to take the second derivative. I recommend taking the derivative of this form here, where it's just a polynomial. That way we don't have to worry about product and chain rule and all that stuff, which is what we'd have to do if we took the derivative of that. And the book agrees with me. Great. So we take our second derivative. That also factors very nicely, giving us a sign diagram over here. And we see that the sign is changing at both points, at 2/3 and at 2. So 2 is our stationary point of inflection. 2/3 is our non-stationary point of inflection. Moving, again, we find the y values of each. Well, we already knew 2, 7. So now we just find the y value of 2/3, rounded to 3 sig figs. Part C, where is the function increasing and decreasing? I've got that right here. It's decreasing from negative infinity to 0, and it's increasing from 0 onward. Part D, where is the function concave up or concave down? That's coming from this sign diagram. It's going to be concave up from negative infinity to 2/3 and from 2 to infinity, and it will be concave down in between those two. Finally, part E, we're going to put this all together. So we're just labeling the 3 points that we worked out before. We don't need any other points. It would be nice if we had x-intercepts, but solving a quartic equation is not the easiest thing to do, so we don't have them here. But we do have a local minimum, a stationary point of inflection, and a non-stationary point, and then we're just going to fill in the shape of the graph matching the information that we worked out up here. It's going to be decreasing and increasing where we said it should be decreasing and increasing, and we're going to have the correct concavity. With practice, you can get a really nice looking sketch this way. And this is what we're going to be expected to do for the IB on these calculus problems on paper 1, where they ask you to sketch a curve. We used to be able to do quite a bit with curve sketching previously. Now we can do even more. I'll just do one more. Here's our function. Part A, find the x-intercept. Okay, so we will find it this time. Well, x-intercept, that means the y value is going to be equal to 0, which means we need 2 to equal 1 over e to the x. That sounds solvable. We'll get an exact answer out of this. It's going to be negative ln of 2. We can approximate that with a decimal if we want. Part B, the y-intercept. Okay, we're setting x equal to 0. That's pretty straightforward. We get y equals 1. Great. Show algebraically that the function is increasing for all x. That means we're going to calculate its derivative and show that it is always positive. So here is our derivative expression. It ends up just being 1 over e to the x. And since e to the x has to be a positive value, 1 divided by that positive is going to be positive. So the function is always increasing. Same idea for part D to show that it's concave down. We calculate the second derivative. We find that it's negative 1 divided by a positive number. So clearly that's going to be negative for all x values. Therefore, this function is always concave down. Part E, why is y equal to a horizontal asymptote? We should be able to work that out just by recognizing that this is an exponential function. The e to the negative x, that has a horizontal asymptote of 0, but this whole thing has been shifted up 2 units. So that's why we've got that as our horizontal asymptote. And then f, we're sketching this thing. Same as before, we've got x-intercept, y-intercept. It's increasing, it's concave down, it's got the asymptote. This picture looks great. Well, now, this one we could have done before calculus because we know what an exponential function should look like, but we can now think of it through the lens of calculus. These two weren't too bad, so we'll look at some more challenging examples in class together, but that's the idea, all right? We're drawing sign diagrams for anything that we possibly can, and then we're going to use that information to figure out what the graph should basically look like. AP loves these questions. In fact, AP will often give you the sign diagrams of some very peculiar looking function. Like they'll just give you the sign diagrams and not give you any other information about it, and then have you try to graph it based on that info. That's a pretty popular free response question type. You can practice those by looking them up online. All the AP free response questions are available for free and totally legally. Just Google AP FRQ and you'll find a ton of them. You just have to find particular questions that you know how to solve, since obviously some of them we haven't learned those topics yet. Anyway, that's all for now. Catch you next time.